What if I told you that beneath everything you see, the stars, the planets, even the air you breathe, there's a hidden chaos, a seething ocean of uncertainty so small, so bizarre, it defies everything we think we know about reality. Picture spacetime not as a smooth, unbroken fabric, but as a frothing, bubbling quantum foam, where space and time themselves twist and churn at scales a million billion times smaller than an atom. This isn't science fiction. This is the cutting edge of our understanding of the universe, a frontier so strange it makes black holes look ordinary by comparison. We're about to dive into 30 of the most mind-bending, spine-tingling theories about quantum foam, ideas that stretch the limits of imagination, where the rules of physics as we know them break down entirely. Some of these theories suggest that within this foam, tiny wormholes flicker in and out of existence, bridging distant parts of the cosmos in an instant. Others propose that entire universes might be bubbling up and vanishing within this quantum storm, like bubbles in a cosmic soda. And then there are the truly wild ideas, like the possibility that the foam itself could hold the key to time travel, or even stranger, that it might be the reason our universe exists at all. This isn't just a journey through abstract science. It's a voyage into the very foundation of reality, where the line between the possible and the impossible blurs. By the time we're done, you'll never look at the universe the same way again. So buckle up, because the deeper we go, the weirder it gets, and the more you'll realize just how much we still have left to discover. Let's begin. The idea that quantum foam could be the very foundation of spacetime flips our understanding of reality upside down. Instead of thinking of space as an empty stage where particles and forces perform, imagine it as something alive, a dynamic, ever-shifting substance where the stage itself is made of untold trillions of microscopic twists and ripples. This isn't just a poetic metaphor, it's a radical shift in physics, one first proposed by the legendary John Wheeler back in the 1950s. He pictured spacetime not as smooth and continuous but as a turbulent sea, where unimaginably tiny fluctuations create fleeting pockets of energy and distortion. At scales so small they defy measurement, far smaller than an atom, even smaller than the nucleus inside it, space and time lose their certainty, they foam. But why would something so chaotic be the bedrock of reality? Think of it like this. If you zoom in close enough on what seems like a smooth sheet of fabric, you'll find threads, knots, and gaps. Zoom in even more, and you'll see those threads are made of fibers, then molecules, then atoms, each level revealing a hidden structure. Quantum foam suggests spacetime works the same way. What looks seamless to us is at its core a storm of probabilistic flickers where particles and forces emerge from the foam itself. Some physicists believe these fluctuations aren't just noise, they're the mechanism by which spacetime stitches itself together, moment by moment, like a cosmic loom weaving existence into being. Cutting-edge theories take this even further. Certain interpretations of quantum gravity propose that without this churning foam, spacetime as we know it couldn't exist. The foam's instability, its constant bubbling, might generate the gravitational fields that hold galaxies together, or even the quantum entanglement that links particles across vast cosmic distances. And if that's true, then every second of our lives, every star in the sky, every law of physics we take for granted, is riding atop this seething quantum undercurrent. It's humbling and thrilling to realize that the universe's grandest structures might owe their existence to the tiniest, most frenzied dance imaginable. One of the most electrifying possibilities hidden within quantum foam is the idea that microscopic wormholes, tiny tunnels through spacetime, might be constantly flickering in and out of existence. These aren't the gargantuan wormholes of sci-fi, capable of ferrying starships across galaxies. They're vanishingly small, lasting only for fractions of a second before the foam's turbulence collapses them again. But their implications are anything but small. According to some theoretical models, these fleeting wormholes could be the universe's shortcuts, threading through the quantum chaos like invisible stitches in the fabric of reality. The math behind this is staggering. In the equations of quantum gravity, spacetime's foam-like nature allows for extreme distortions, tiny regions where space pinches into a tunnel, connecting two distant points in an instant. Think of it like bubbles forming in boiling water. Most pop immediately, but what if some persist just long enough to create a bridge? While these wormholes would be too unstable and minuscule for anything to traverse them, their existence hints at something profound. The universe might be threaded with hidden connections, a labyrinth of ephemeral passageways we're only beginning to imagine. Even wilder is how these wormholes could tie into faster-than-light travel. If they could be stabilized, perhaps by some advanced technology or exotic matter, they might offer a way to bypass the cosmic speed limit set by light. Imagine a spacecraft darting through a wormhole instead of crossing the vast emptiness between stars, reaching Alpha Centauri not in years but in an eye blink. It's speculative but not impossible. Recent theoretical work like loop quantum gravity models suggests that under the right conditions, these quantum wormholes might be coaxed into staying open longer, creating highways through spacetime itself. But the real mind bender, these wormholes might not just connect distant places, they could link entirely different universes. Some interpretations of string theory and the multiverse hypothesis propose that every time a wormhole forms in the foam, it briefly bridges our universe with another, a parallel reality with its own laws, its own history. For that fleeting moment, the boundaries between worlds dissolve and anything, or anyone could, in theory, slip through. It's a dizzying thought that every second countless unseen doorways are opening and closing all around us, leading to realms beyond our wildest dreams. Of course, none of this is proven. Quantum foam and its wormholes remain locked in the realm of theory, their existence inferred from the edges of our equations rather than direct observation. But that's what makes it so thrilling. If even a fraction of these ideas hold water, the universe is far stranger, far more interconnected than we ever dared to suspect. And somewhere in that churning quantum sea, the answers might be waiting just out of reach, but not forever. What if the same quantum foam that twists spacetime at microscopic scales is also pulling the entire universe apart? This startling possibility suggests that the chaotic energy fluctuations in the foam might be the hidden engine behind dark energy, the mysterious force accelerating the cosmos's expansion. Picture this: every cubic centimeter of empty space, no matter how seemingly placid, is actually a maelstrom of virtual particles popping in and out of existence, a phenomenon known as vacuum energy. When physicists calculate how much energy this quantum frenzy should contain, they hit a problem. The numbers are absurdly large, predicting an expansion rate that would have torn the universe to shreds billions of years ago. Yet observations show dark energy's effect is far weaker, a discrepancy so glaring it's called the worst prediction in physics. Here's where quantum foam offers a tantalizing clue. Some theorists propose that the foam's structure could act like a cosmic dampener, its turbulent geometry cancelling out most of this vacuum energy, leaving behind just a faint residue, the very dark energy we detect. Imagine blowing up a balloon covered in tiny wrinkles. As it expands, the wrinkles smooth out, subtly altering how the surface stretches. Similarly, as spacetime expands, the foam's jittery nature might dilute its own energy, leaving just enough to nudge galaxies apart. Not everyone agrees. Alternative models suggest dark energy arises from entirely different mechanisms, like an unknown field permeating space or modifications to Einstein's gravity. Skeptics point out that marrying quantum foam to cosmic expansion requires exotic physics untested by experiment, but supporters counter that upcoming probes, like next-generation gravitational wave detectors, could spot subtle imprints of foam like spacetime in ripples from colliding black holes. Others are hunting for minute variations in the speed of light across space, which a frothy vacuum might cause. The stakes couldn't be higher. If quantum foam's fingerprints are found in dark energy, it would bridge the greatest chasm in physics, uniting the infinitesimally small with the cosmically vast. We'd finally understand why the universe didn't explode at its birth, why it's spreading faster now, and whether this acceleration is eternal or a fleeting phase in a deeper cycle of cosmic upheaval. Until then, the foam remains both a puzzle and a promise, a reminder that the emptiest corners of space might hold the keys to the universe's fate. Time itself might not be the steady, unbroken river we perceive down in the quantum foam. It could be more like a choppy sea, full of unpredictable ripples and eddies. At scales so tiny they make atoms look like giants, spacetime's foam-like structure might introduce bizarre time distortions, where moments stretch, compress, or even flicker unpredictably. This isn't just science fiction. Experiments with ultra-precise atomic clocks have already shown that time ticks differently depending on altitude or motion, proof that gravity and velocity warp time. But quantum foam suggests something even stranger, that time's flow might be inherently jittery at its most fundamental level. Loop quantum gravity, a leading theory aiming to reconcile Einstein's relativity with quantum mechanics, paints a tantalizing picture. In this framework, spacetime isn't smooth but granular, woven from tiny, indivisible atoms of space and time. These grains could shift and churn in the quantum foam, creating fleeting pockets where time speeds up, slows down, or even stutters. Imagine a stopwatch that, if you could zoom in close enough, sometimes misses a few Planck-length seconds, the smallest meaningful units of time. These microscopic hiccups would normally average out to the steady time we experience, like how a blurry photograph hides individual pixels. But under extreme conditions like near a black hole's singularity or in the seething foam of the early universe, these time fluctuations might become noticeable, warping reality in ways we're only beginning to grasp. The implications are staggering. If time isn't perfectly uniform at quantum scales, it could explain why atomic clocks occasionally disagree with predictions, their ticks subtly thrown off by spacetime's hidden turbulence. Some physicists speculate these tiny time warps might even influence the arrow of time itself, the mysterious reason why we remember the past but not the future. Normally, entropy drives time's forward march, but quantum foam could be stirring the pot, introducing randomness that nudges events in one direction. It's a radical idea that the flow of time we take for granted might emerge from countless microscopic distortions in the foam, like a river's current emerging from countless swirling eddies. And then there's the wild card wormholes. If quantum foam spawns fleeting tunnels through spacetime, these could twist time in ways that defy intuition. A wormhole might briefly connect not just two places but two moments, creating closed time-like curves where cause and effect loop back on themselves. While stable time travel remains speculative, the foam's chaotic nature suggests that on the smallest scales, time might not always move forward. Particles could momentarily zigzag through time, blurring the line between past and future. Loop quantum gravity simulations even hint that in the foam's deepest layers, the concepts of before and after might lose meaning entirely, replaced by a network of events without a fixed sequence. Of course, testing these ideas is a monumental challenge. Current technology can't probe the Planck scale where these effects would dominate, but next-generation quantum sensors and gravitational wave detectors might one day catch whispers of spacetime's graininess, offering clues. Until then, the foam remains a realm of thrilling possibilities, a reminder that time, the most familiar part of our lives, might be the universe's greatest illusion, stitched together from a storm of quantum uncertainties. The next time you check your watch, remember, down in the foam, time dances to its own chaotic rhythm. Black holes have long been the universe's ultimate vault, swallowing stars, light, and even information itself, seemingly without a trace. But what if their deepest secrets aren't lost forever, just hidden in plain sight, etched into the quantum foam at their edges? This dazzling idea springs from the holographic principle, a radical theory suggesting that all the information contained within a black hole's volume might be encoded on its two-dimensional surface, like a cosmic barcode written in spacetime's tiniest fluctuations. And the medium for that encoding, the seething quantum foam at the event horizon. Think of it this way: when matter falls into a black hole, it doesn't just vanish. According to quantum mechanics, information can't be destroyed. It has to go somewhere. The holographic principle proposes that as objects cross the event horizon, their details get scrambled and imprinted onto the foam's chaotic swirls, like messages carved into the froth of a crashing wave. Each Planck-sized bubble in the foam could act like a pixel, storing bits of data in the way it twists or vibrates. Over time, these microscopic imprints might collectively hold the entire history of what the black hole consumed, a library of lost stars written in spacetime's quantum alphabet. This isn't just poetic speculation. The math behind black hole thermodynamics points directly to this possibility. Stephen Hawking's groundbreaking work showed that black holes emit radiation now named after him and slowly evaporate. But here's the catch: if they vanish entirely, what happens to all that swallowed information? The holographic principle offers an elegant escape from this paradox. If the data is stored in the foam at the horizon, it could radiate outward via Hawking radiation, piece by piece, like a cosmic hard drive slowly decrypting its contents back into the universe. Skeptics push back, of course. Some argue that quantum foam alone can't account for the staggering complexity of black hole entropy, the measure of a black hole's hidden information. Others propose competing theories, like firewalls, violent walls of energy at the event horizon that would destroy incoming matter long before it could encode anything. But supporters counter that firewalls violate Einstein's equivalence principle, which states that free falling into a black hole should feel uneventful until it's too late. Quantum foam, by contrast, offers a subtler solution, weaving information into spacetime's fabric without breaking physics as we know it. The implications are staggering. If quantum foam truly stores black hole data, it could mean that reality itself operates like a hologram, with the three-dimensional universe we experience projecting from a two-dimensional boundary. It's a notion that reshapes not just how we see black holes, but the very nature of existence. Future experiments like gravitational wave observations of merging black holes or lab-scale simulations of holographic systems might one day test this. Until then, the foam remains a tantalizing cipher, a cosmic Rosetta Stone waiting to reveal whether the universe's darkest secrets are written, quite literally, in its ripples. The very first moments of the universe may have been shaped by quantum foam's chaotic churn, a storm of microscopic spacetime bubbles so violent it could have launched the entire cosmos into hyperdrive. This theory suggests that the rapid expansion we call cosmic inflation wasn't caused by some exotic field or particle, but by the raw, seething energy of spacetime itself fragmenting and recombining at the smallest scales. Picture the Big Bang not as a single explosive event, but as a chain reaction. A quantum foam so unstable, its fluctuations tip the universe into exponential growth, stretching a speck smaller than a proton to cosmic proportions in less than a trillionth of a second. How does this differ from classic inflationary models? Traditional inflation relies on a hypothetical, inflatoned field, a kind of cosmic energy syrup that stretched space smoothly. But foam-driven inflation replaces that with something far wilder, spacetime's own turbulent geometry. Imagine blowing up a balloon covered in microscopic bumps. Instead of expanding evenly, those bumps could trigger localized bursts of growth, like tiny engines flaring across the universe's fabric. Supporters argue this solves a major puzzle: why inflation started and stopped so abruptly. The foam's natural frothiness would have regions where quantum fluctuations piled up, creating pockets of instability, perfect conditions for runaway expansion. Once those pockets smoothed out, inflation would slam the brakes, leaving behind the universe we see. The multiverse angle is even more mind-bending. If inflation was driven by quantum foam, it might not have been a one-time event. Chaotic foam conditions could still be bubbling up new universes right now in the depths of space, each with its own physics. Some versions of string theory suggest these baby universes pinch off like soap bubbles from a froth, inflating into their own separate realities. It's a cosmic spin on natural selection. Universes with the right foam dynamics survive long enough to spawn stars and life, while others collapse or drift into oblivion. Critics aren't convinced. Without direct evidence of quantum foam's role, they argue, this remains speculative, especially when traditional inflation fits current data so well. But foam enthusiasts counter that subtle signatures might linger in the cosmic microwave background, the afterglow of the Big Bang. Future telescopes could hunt for unusual patterns in this ancient light, traces of spacetime's primordial turbulence. Others suggest gravitational waves from the universe's first moments might carry echoes of foam-driven expansion, a whisper of chaos frozen in spacetime's ripples. What's at stake? If quantum foam did power inflation, it would mean our universe wasn't just born in chaos, it was born from it. The same frothy violence that twists spacetime at the smallest scales might have set the stage for galaxies, planets, and life itself. And if foam keeps spawning new universes, we could be living in just one bubble among countless others, adrift in a sea of quantum possibility. It's a humbling thought that the vast, orderly cosmos we call home might owe everything to the roiling anarchy of the very small. Quantum foam might hold the answer to one of physics' greatest mysteries: why the quantum world behaves so bizarrely at tiny scales, while the classical world we experience feels solid and predictable. This divide, called the measurement problem, has puzzled scientists for decades. When a particle like an electron isn't being observed, it exists in a superposition, spread out like a wave with multiple possible states. But the moment we measure it, this quantum weirdness collapses into a single, definite outcome. Decoherence theory suggests this collapse isn't magical, it's caused by interactions with the environment. But here's where quantum foam kicks in. The foam's chaotic fluctuations could be the ultimate decoherence machine, constantly jostling quantum systems into classical behavior. Think of it like trying to balance a pencil on its tip in the middle of an earthquake. No matter how carefully you place it, the tremors will eventually knock it over. Similarly, spacetime's foam-like structure might bombard particles with microscopic turbulence, disrupting their delicate quantum states before they can sustain superposition for long. Experiments with ultra-cold atoms isolated from most environmental noise support this idea. Even in near-perfect vacuums, quantum systems eventually decohere, hinting that something deeper is at play. Some physicists propose this something is Planck-scale noise from quantum foam, shaking particles into classicality like static drowning out a radio signal. The implications are profound. If foam-induced decoherence is real, it could explain why we never see Schrödinger's cat both dead and alive. The foam's relentless churn forces reality to pick a side far too quickly for macroscopic weirdness to appear. This would bridge the gap between quantum theory and everyday experience without invoking conscious observers or hidden variables. Teams are now designing tabletop experiments to test this directly, using entangled particles shielded from conventional decoherent sources. If fluctuations in their behavior match predictions from foam models, it could mean we've found quantum mechanics' missing link, not in particles or forces, but in spacetime's restless grain. Critics argue foam decoherence is untestable since Planck-scale effects are so minuscule, but supporters counter that cumulative impacts over time could leave measurable traces, like subtle anomalies in how entangled particles lose sync. Others suggest looking for foam's fingerprints in the cosmic microwave background, where primordial spacetime turbulence might have left statistical ripples. Either way, the hunt is on, because if quantum foam truly decoheres reality, it means the universe itself is constantly measuring everything. It's fractal turbulence writing the boundary between the quantum and classical worlds with every flickering Planck-length bubble. Even the emptiest void of space is far from empty thanks to quantum foam. It's a seething nursery for particles that flicker in and out of existence like sparks in a cosmic fire. These are virtual particles, ephemeral pairs of matter and antimatter that borrow energy from spacetime itself, popping into being for fractions of a second before annihilating each other. Normally, they vanish too quickly to leave a trace, but in the roiling chaos of quantum foam, these particles get a chance to dance on the edge of reality, with consequences that ripple across the universe. Here's how it works. Imagine quantum foam as a stormy ocean where waves constantly crash and churn. In that turbulence, tiny bubbles form regions where spacetime's energy fluctuations become so intense they briefly conjure particle pairs from nothing. It's like shaking a soda bottle and watching bubbles erupt. The foam's agitation provides the energy needed for these particles to emerge. Most collide and vanish instantly, but near a black hole's event horizon, something extraordinary happens. The extreme gravity can wrench these pairs apart, flinging one particle into the abyss while the other escapes as radiation. Hawking radiation, the very glow that slowly evaporates black holes. This isn't just theoretical. Experiments with the Casimir effect, where two metal plates placed microscopically close in a vacuum feel an invisible force pushing them together, prove virtual particles exist. The plates squeeze out certain particle fluctuations, creating an imbalance that drives them inward. Quantum foam amplifies this phenomenon, suggesting that spacetime's frothiness might be the engine behind zero-point energy, the lowest possible energy state of a quantum system. Picture a car engine idling. Even at rest, it hums with latent power. The universe does the same, its empty space crackling with energy borrowed from the foam's ceaseless churn. Some physicists speculate this zero-point energy could be harnessed, a sci-fi dream of limitless power drawn from the vacuum itself. The hurdles are monumental, though. The energy locked in quantum foam is unimaginably diffuse, like trying to collect raindrops one molecule at a time. Worse, tinkering with spacetime's fabric risks destabilizing the very stage reality plays on. Yet the tantalizing possibility remains. If we could tap even a fraction of this energy, it would rewrite the future of civilization. Of course, skeptics caution that virtual particles might just be mathematical tricks, not real physical entities. But Hawking radiation's discovery lends weight to their reality, and if quantum foam truly births them, it means the universe is constantly recycling energy at the smallest scales, a hidden economy where spacetime itself is the currency. Every second, countless particles rise and fall in this invisible storm, shaping everything from black holes to the vacuum's whisper-thin energy. It's a reminder that nothing, not even empty space, is ever truly at rest. What if the quantum foam beneath our feet isn't the foundation of reality, but the glitches in its code? This is the spine-tingling core of the simulation hypothesis, the idea that our universe might be an artificial construct, with spacetime's frothy turbulence serving as the pixelated grain of an unfathomably advanced simulation. Think of it like zooming in on a video game's texture until you see the individual pixels. At the smallest scales, even the most realistic simulation would reveal its underlying structure. And some theorists argue that quantum foam, with its unpredictable fluctuations and Planck-sized granularity, fits that description perfectly. The math behind this is startlingly elegant. Every simulation has computational limits, finite memory and processing power. If you're building a universe, you'd need to discretize spacetime to conserve resources, avoiding infinite calculations. Enter the Planck length and Planck time, the smallest possible units of space and duration where quantum foam's chaos reigns. These aren't arbitrary numbers, they're the universe's apparent resolution limits, the points beyond which measurements lose meaning. To simulation advocates, this looks suspiciously like a built-in frame rate, the granularity required to render reality without overloading the system. Even the holographic principle, the idea that all 3D information can be encoded on a 2D surface, mirrors how modern simulations optimize data storage, like a cosmic version of texture compression. But critics pounce on flaws. If we're in a simulation, why would the creators leave such obvious artifacts as quantum foam? Wouldn't they smooth over the seams? Some physicists counter that the foam's behavior isn't glitchy. It's mathematically inevitable in any quantum gravitational framework, simulated or not. Others note that the simulation hypothesis is unfalsifiable by design. It's a metaphysical stance, not a scientific one. After all, how could you prove you're not inside a simulation when all your tools, even your own cognition, would be part of the program? Yet tantalizing clues linger. Certain quantum phenomena, like entanglement's instant correlations across space, resemble how a simulation might optimize by referencing global variables rather than calculating local interactions. Even the infamous double-slit experiment, where particles act as waves until observed, could reflect a universe that only renders precise details when needed. A cosmic, don't render what isn't observed, setting to save processing power. The debate takes a philosophical turn when considering motives. If our universe is simulated, who's running it? Ancestor simulations? Alien civilizations? A future version of ourselves? And why create a cosmos with black holes, quantum foam, and dark matter, unless those features are emergent bugs or deliberate constraints? The unnerving truth is that even if we are in a simulation, the foam might be less a flaw and more a feature, the unavoidable noise of a system vast enough to host conscious beings who can ponder their own existence. Ultimately, whether quantum foam is the canvas of reality or the grit in its gears, the simulation hypothesis forces us to confront profound questions. If spacetime has a resolution limit, does that imply something or someone set it? Or is it simply the universe's way of reminding us that at the deepest levels, certainty dissolves into a beautiful, chaotic dance? Either way, quantum foam remains the perfect Rorschach test for reality. What we see in its turbulence says as much about us as it does about the cosmos. Quantum foam isn't just a curiosity, it could be the ultimate testing ground for the holy grail of physics, a unified theory of quantum gravity. For decades, scientists have struggled to bridge the gap between Einstein's general relativity, which governs the cosmos on large scales, and quantum mechanics, which rules the subatomic realm. These frameworks work flawlessly in their own domains, but when they collide, like near a black hole's singularity or in the universe's first moments, their equations explode into nonsense. Quantum foam might hold the key to reconciling them, offering a microscopic lab where spacetime's smooth curves fracture into quantum frenzy. String theory, one of the leading contenders, paints a mesmerizing picture. It suggests that the foam's turbulence isn't random noise but the vibrations of unimaginably tiny strings, each threading through higher dimensions we can't perceive. These strings wouldn't just wiggle, they'd twist spacetime into knots, creating the foam's characteristic froth. At certain energies, their vibrations might even stabilize microscopic wormholes or warp the fabric of reality into Calabi-Yau shapes, intricate geometries that could explain why we experience only 4 dimensions while others remain curled up, hidden in the foam's folds. But string theory isn't the only player. Causal set theory takes a radically different approach, proposing that spacetime isn't continuous but built from discrete, indivisible atoms of existence. Imagine the universe as a cosmic necklace, each bead representing a moment in spacetime, linked only to its immediate neighbors. Quantum foam, in this view, emerges from the gaps between these beads, a froth of missing connections where causality itself blurs. This could explain why time seems to flow. Our perception of continuity might be an illusion emerging from the foam's chaotic stitching of these atomic moments. Then there's loop quantum gravity, which envisions spacetime as a network of woven threads, intersecting and tangling to form a dynamic, granular fabric. In this model, quantum foam isn't just foam. It's a literal tapestry of loops where every knot and crossover twists gravity into existence. When these loops tighten or fray, they could create the extreme conditions seen in black holes or the Big Bang, places where relativity's smooth spacetime shatters into quantum fragments. The stakes couldn't be higher. If any of these theories correctly describe foam's structure, they'd rewrite physics from the ground up. String theory's extra dimensions could unveil hidden layers of reality. Causal sets might prove time is an emergent property, not a fundamental one. Loop quantum gravity could reveal how space itself is woven from pure relationships. But the real magic lies in their shared prediction. That quantum foam isn't just background noise, it's the active ingredient stitching the universe together. Testing these ideas isn't easy, but physicists are ingenious. Some hunt for imprints of foam in high-energy cosmic rays, which might scatter off spacetime's granularity like pebbles skipping across a bumpy pond. Others analyze quantum entanglement, seeking subtle deviations that could betray foam's hidden geometry. There's even hope that next-generation gravitational wave detectors could catch whispers of Planck-scale jitters in ripples from colliding neutron stars. What's breathtaking is how these theories reframe the foam's chaos. It's not a flaw in reality, it's the signature of a deeper order, a cosmic code waiting to be cracked. And if we succeed, we won't just solve a puzzle, we'll glimpse the universe's blueprints written in the froth of spacetime itself. Could consciousness itself be shaping the quantum foam beneath our feet? This radical idea suggests that our minds might not just observe reality, they could actively sculpt it, collapsing the foam's chaotic fluctuations into the stable world we experience. At the heart of this theory lies orchestrated objective reduction, or a hypothesis proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They argue that quantum processes in the brain's microtubules, tiny protein structures inside neurons, interact with spacetime's foam-like nature, turning probabilistic quantum possibilities into definite perceptions. It's a wild claim that every thought, every moment of awareness might be a dialogue with the universe's smallest scales. The math behind or is as elegant as it is controversial. Penrose theorized that quantum superpositions in microtubules, states where particles exist in multiple positions at once, can't endure indefinitely. Under gravity's influence, they eventually collapse, with the foam's turbulence acting as the trigger. Each collapse, he proposed, is a moment of conscious experience, a tiny click in the machinery of mind. Hameroff took this further, suggesting these collapses could be orchestrated by biological processes, creating the seamless stream of awareness we take for granted. Together, they paint consciousness not as a passive byproduct of brain chemistry, but as an active participant in spacetime's quantum dance. Skeptics aren't shy about poking holes. Many physicists argue that the brain is too warm and noisy for delicate quantum states to survive long enough to matter. Decoherence, the process where quantum systems lose coherence due to environmental interference, would shred these effects almost instantly. Even proponents admit the idea is speculative, with no direct evidence yet linking microtubules to quantum gravity, but or isn't without tantalizing clues. Anesthetic gases, which selectively erase consciousness while leaving other brain functions intact, seem to target microtubules, hinting they play a special role in awareness. Meanwhile, lab experiments have shown quantum coherence in photosynthesis, proving biological systems can harness quantum effects, at least briefly, the wildest implication. If consciousness does interact with quantum foam, it might mean reality isn't fully real until observed, echoing the famous paradox of Schrödinger's cat. Some interpretations go further, suggesting that in the absence of observation, spacetime's foam remains a blur of possibilities, only settling into concrete form when a conscious mind looks. This isn't just philosophy, it's testable. Or predicts that if microtubules are quantum devices, disrupting them should alter consciousness. Experiments using ultrasound to vibrate microtubules have shown strange effects on perception, though critics argue these could have classical explanations. Future tests might involve cooling brains to near absolute zero, where quantum effects could persist long enough to observe. Of course, mainstream science remains deeply divided. Many view or as a beautiful but unproven metaphor, a placeholder until harder evidence emerges. Others see it as the first hint of a deeper truth, that mind and universe are entwined in ways we're only beginning to glimpse. Whether or not consciousness shapes quantum foam, the mere possibility forces us to reconsider our place in the cosmos. Are we passive observers of a pre-written reality or active collaborators, weaving the fabric of spacetime with every thought? The answer, like the foam itself, remains tantalizingly out of focus. Quantum entanglement, the eerie phenomenon where particles instantaneously influence each other across vast distances, defies everything we know about space and time. Einstein famously called it spooky action at a distance, a puzzle that still challenges physicists today. But what if the answer lies in the quantum foam itself? Some theories propose that spacetime's turbulent, frothy nature isn't just background noise. It could be the hidden medium that links entangled particles, weaving an invisible web beneath the fabric of reality. Picture two entangled electrons spinning in sync, separated by light years. Under classical physics, any communication between them would need to break the cosmic speed limit, the speed of light. Yet experiments confirm they coordinate instantly, as if space and time don't exist for their connection. One daring explanation suggests the foam's microscopic wormholes or Planck-scale fluctuations could create fleeting bridges between them, allowing information to tunnel through spacetime's chaos without traversing the distance in between. Imagine two people whispering through a convoluted maze. If the walls between them constantly shift and warp, their voices might find shortcuts invisible to an outside observer. In this view, entanglement isn't magic. It's spacetime's plumbing at work. This idea collides with other interpretations like pilot wave theory, which proposes that particles are guided by hidden waves carrying quantum information. Pilot wave avoids spooky action by suggesting everything is pre-connected through these waves, but it struggles to explain entanglement's randomness. Quantum foam offers a twist. Instead of pre-existing waves, the foam's dynamic turbulence could generate real-time pathways, adapting instantaneously as particles interact. It's the difference between a pre-written script and an improv performance where spacetime itself is the stagehand, rearranging the set mid-scene. Critics argue that foam-mediated entanglement pushes speculative physics to its limits. Without direct evidence of foam's structure, it's hard to test whether these Planck-scale bridges exist. Yet supporters point to tantalizing hints, like anomalies in high-energy particle collisions that hint at extra dimensions, potential fingerprints of foam's deeper architecture. Others note that entanglement's fidelity, how reliably particles stay linked, might degrade over vast distances if spacetime's foam introduces noise, a prediction future quantum satellite experiments could probe. The debate touches the heart of quantum mechanics. Is the universe fundamentally interconnected with foam as the glue, or are we missing something even stranger? What's clear is that quantum foam forces us to rethink locality, the idea that objects are only influenced by their immediate surroundings. If entanglement rides the foam's turbulent currents, then beneath the calm surface of space, there's a hidden vibrancy stitching everything together, a reminder that the universe is far more intimate than it appears. The universe should have torn itself apart within moments of the Big Bang. At least, that's what the math says. When physicists calculate how much energy should be boiling in the vacuum of space due to quantum foam's ceaseless particle creation and annihilation, the numbers are catastrophically large. We're talking about a value 10 to the power of 120 times greater than what we actually observe, a discrepancy so vast it's been called the worst prediction in the history of physics. Yet here we are in a stable cosmos where galaxies spin and life thrives. How quantum foam might hold the key to this enigma, offering a way for spacetime's turbulence to cancel out its own destructive potential. Imagine the vacuum as a stormy ocean. Quantum foam's fluctuations are like waves crashing in all directions, each carrying immense energy. Normally, these waves would add up to a tsunami capable of ripping spacetime apart. But what if the foam's chaotic nature creates hidden interference patterns, like waves colliding in just the right way to cancel each other out? Some theories suggest that spacetime's granular structure, the fact that it's not smooth but made of tiny, jittery pixels at the Planck scale, introduces a natural dampening effect. The foam's turbulence could act like a cosmic muffler, silencing most of its own cacophony and leaving behind only the faint hum we detect as dark energy. This isn't just wishful thinking. Certain interpretations of loop quantum gravity hint at a mechanism where foam, like spacetime, knits itself together in a way that neutralizes excess energy. Think of it like a tightly woven fabric. Pull one thread too hard, and the surrounding weave redistributes the tension. Similarly, as quantum foam's bubbles stretch and twist, their interactions might spread vacuum energy so thinly across spacetime that its explosive potential never fully materializes. It's a delicate balancing act, one where the universe's survival depends on the foam's ability to self-regulate. The implications are staggering. If quantum foam truly tames vacuum energy, it would solve one of cosmology's most glaring paradoxes while revealing a hidden harmony in the chaos. But skeptics raise valid concerns. Why does the cancellation leave just enough residual energy to drive cosmic acceleration? And if foam's structure is the answer, why haven't we detected its fingerprints in precision experiments? Some theorists argue that the foam's effects might be too subtle for current technology, like trying to hear a whisper in a hurricane. Others propose that dark energy isn't from the foam at all, but an entirely separate field or a flaw in Einstein's equations. The quest for answers is heating up. Next-generation telescopes hunting for anomalies in the cosmic microwave background could spot traces of early spacetime turbulence, while ultra-precise atomic clocks might detect minute variations in time's flow caused by foam's granularity. Even gravitational wave observatories could stumble upon clues. Ripples from ancient black hole collisions might carry imprints of the foam's texture, like waves revealing the shape of a pond's surface. What's clear is this: the vacuum catastrophe isn't just a math error. It's a screaming hint that our understanding of reality is incomplete. Quantum foam, with its chaotic beauty, might be the universe's way of whispering a deeper truth, that even emptiness is alive, brimming with hidden forces we're only beginning to decipher. And if we listen closely, we might finally hear the cosmos explaining itself. The Big Bang is often pictured as an infinitely dense, infinitely hot singularity, a point where all the laws of physics break down. But what if that singularity never actually existed? Quantum foam might have rewritten the very first moment of our universe, replacing that mathematical monstrosity with something far stranger, a cosmic bounce where spacetime's frothy turbulence cushioned the blow of creation itself. Loop quantum cosmology, a radical offshoot of loop quantum gravity, paints a breathtaking alternative to the classic Big Bang story. Instead of an all-crushing singularity, it proposes that the universe sprang from a hyper-compressed state where quantum foam's granular structure couldn't be squeezed any further. Picture a spring pressed to its limit. Just before it snaps, it recoils. In this model, gravity, which normally pulls matter together, becomes repulsive at extreme densities thanks to quantum foam's frenzied geometry. The universe didn't explode from nothing. It rebounded like a phoenix rising from the ashes of a previous cosmic cycle. This big bounce solves one of physics' biggest headaches, the singularity problem, where Einstein's equations predict infinities that make no physical sense. The implications are staggering. If the foam's churn smoothed out the Big Bang, traces of that pre-bounce universe might still linger. Some models suggest faint swirls in the cosmic microwave background. The afterglow of creation could carry echoes of that earlier epoch, like ripples from a stone tossed into a pond before time began. Others speculate that if the universe cycles through endless bounces, each incarnation might tweak the laws of physics slightly, explaining why our cosmos seems fine-tuned for life. Critics argue this is speculative without observational proof. It's hard to favor a bounce over the classic Big Bang, but supporters counter that singularities are mathematical red flags, screaming that our theories are incomplete. Quantum foam, by contrast, offers a way out, transforming the universe's birth from a baffling rupture into an elegant transition. Future telescopes analyzing gravitational waves from the universe's infancy could settle the debate. If they detect signatures of a bounce, it might mean our cosmos is just the latest chapter in an endless story, written in the foam's ever-shifting script. The real magic: this isn't just about the past. If quantum foam enabled a bounce once, it could happen again. Far in the future, if our universe collapses toward a big crunch, the same repulsive foam physics might trigger another rebirth. Suddenly, the cosmos feels less like a one-time event and more like a heartbeat, pulsing to the rhythm of spacetime's deepest chaos. Dark matter has long been the universe's most frustrating ghost, invisible, untouchable, yet holding galaxies together with its gravitational embrace. For decades, scientists have chased particles like WIMP or actions as potential dark matter candidates. But what if the answer isn't a particle at all? What if dark matter is simply the universe's quantum foam bubbling unevenly, creating pockets of hidden mass where spacetime itself is slightly denser? This radical idea flips the script on conventional dark matter theories. Instead of invoking exotic particles, it suggests that quantum foam's turbulence isn't perfectly uniform. Certain regions might froth more intensely, subtly warping gravity without any actual matter present. Picture a rubber sheet covered in microscopic bumps. From a distance, it looks flat, but up close, those imperfections create tiny hills and valleys that could deflect a rolling marble. Similarly, if spacetime's foam has thicker knots where fluctuations pile up, their extra gravitational pull could mimic the effects of dark matter, explaining why galaxies rotate faster than visible matter alone should allow. How does this differ from WIMP? Traditional dark matter models rely on undiscovered particles that barely interact with light but cluster around galaxies like invisible scaffolding. The foam theory, by contrast, requires no new particles, just spacetime's own uneven texture. It's the difference between sprinkling glitter on a canvas versus the canvas itself having raised brushstrokes. Skeptics argue that foam fluctuations would need to be improbably large to match dark matter's observed effects, but supporters counter that quantum gravity's nonlinearity could amplify tiny Planck-scale variations into cosmic-scale ripples. The most intriguing evidence comes from galactic rotation curves. Stars at a galaxy's outskirts orbit so fast that visible matter can't hold them, yet foam density variations could provide the extra gravitational grip needed. Unlike WIMP, which should form smooth halos around galaxies, foam's lumpiness might also explain oddities like ultra-diffuse galaxies that appear almost devoid of dark matter. If these galaxies exist in regions where spacetime's foam is unusually smooth, their rotation would match visible mass predictions perfectly, a feat WIMP models struggle with. Challenges remain, of course. Quantum foam's gravitational influence is notoriously hard to calculate, and no experiment has yet measured its hypothetical density variations. Critics also note that foam-based dark matter would interact differently with galaxy clusters than particle-based models, potentially conflicting with gravitational lensing observations. But upcoming telescopes like the Vera Rubin Observatory could settle the debate by mapping dark matter's distribution in unprecedented detail. If its arrangement matches foam turbulence predictions rather than particle simulations, we might be witnessing not invisible matter, but the hidden topography of spacetime itself. The beauty of this idea lies in its simplicity. Dark matter has always been a placeholder, a something we know must exist but can't see. If quantum foam explains it, the universe's greatest mystery might not be missing matter at all, but the restless, uneven churn of the stage beneath our feet. Light doesn't travel through empty space. It dances through quantum foam, and that dance might leave faint footprints across the cosmos. One of the most intriguing consequences of spacetime's turbulent, frothy nature is how it could subtly bend and scatter light over vast distances. Imagine shining a flashlight through thick fog. The beam spreads and blurs as photons ricochet off water droplets. Now replace the fog with spacetime's foam, and you've got a cosmic version of the same phenomenon. Except instead of water droplets, light encounters Planck-scale bubbles of warped spacetime, each one potentially nudging a photon off course. Over billions of light years, these microscopic deflections could add up, distorting our view of the universe's most luminous objects, quasars, gamma-ray bursts, and even the cosmic microwave background. Astrophysicists have a name for this effect: spacetime foam-induced dispersion. The idea is that high-energy photons, those packing the shortest wavelengths, should interact more strongly with the foam's tiniest fluctuations. Think of it like a speedboat versus a kayak in choppy waters. The speedboat, a high-energy gamma-ray photon, hits every wave, while the kayak, a low-energy radio wave, glides smoothly over them. If foam exists, gamma rays from distant cosmic explosions should arrive slightly later than their lower-energy counterparts, as if they've taken a more turbulent path through spacetime's quantum rapids. The hunt for this signature is already underway. Telescopes like the Fermi Gamma-Ray Space Telescope have spent years scrutinizing gamma-ray bursts from the edge of the observable universe, searching for delays between different wavelengths that could betray spacetime's granularity. So far, the results are tantalizing but inconclusive. Some bursts show hints of dispersion, while others don't. This could mean the foam's effects are subtler than predicted, or that we're seeing statistical noise. But there's another possibility. The foam might not be uniform. Just as ocean waves vary from calm swells to violent breakers, spacetime's turbulence could be patchy, with dense knots of foam scattered across the cosmos, leaving some light paths pristine while others twist like funhouse mirrors. Critics argue that alternative explanations like interstellar dust or magnetic fields could mimic foam's dispersive effects. Yet supporters counter that certain anomalies, like unexpectedly sharp images of distant quasars, defy conventional physics unless spacetime is smoother than quantum theory predicts. The debate hinges on a deeper question: does spacetime foam leave fingerprints we can actually see, or is it too delicate to detect with current technology? The stakes are high. If foam's imprint on light is real, it wouldn't just validate quantum gravity, it would force us to rewrite astronomy textbooks. Distant galaxies might not be exactly where they appear, their light subtly deflected by foam's invisible currents. Even our measurements of cosmic expansion could need recalibration if spacetime's texture subtly alters the redshift of ancient starlight. Future observatories like the Cherenkov Telescope Array aim to settle the debate by capturing ultra-high-energy photons from across the universe. If they find evidence of foam's turbulence, it would mean every star we see is filtered through a quantum lens, a reminder that reality, even at its most pristine, is never quite what it seems. The universe might be teeming with self-aware minds that flicker into existence for just a fraction of a second, not in distant galaxies, but in the quantum foam beneath our feet. This bizarre notion, known as the Boltzmann brain paradox, takes the foam's chaos to its ultimate extreme. Imagine spacetime's turbulence not just spawning particles or wormholes, but entire conscious experiences, a fleeting thought, a half-formed memory, or even the illusion of an entire lifetime, all conjured from the void by pure chance. It sounds like science fiction, but it's a serious philosophical headache born from thermodynamics and quantum mechanics. The paradox starts with a simple question. In an infinite or near-eternal universe where quantum foam churns endlessly, shouldn't sheer randomness eventually assemble a self-aware observer? After all, the foam already creates virtual particles from nothing. Given enough time, could it stitch together atoms, neurons, even a fully functioning brain? Ludwig Boltzmann, the 19th century physicist who first grappled with these ideas, realized that statistically, a random fluctuation producing a lone, disembodied mind is infinitely more likely than the ordered universe we see around us. That's the unsettling core of the paradox. Why are we here in a vast, structured cosmos, rather than isolated brains hallucinating reality from the foam's noise? Quantum foam cranks this puzzle to 11. If spacetime is fundamentally frothy and probabilistic, then at scales smaller than atoms, the distinction between something and nothing blurs. In that maelstrom, Boltzmann brains wouldn't just be hypothetical, they'd be inevitable. Some theories even suggest these phantom minds could outnumber real observers like us by an unimaginable margin, popping in and out of existence like bubbles in a boiling pot. The implications are dizzying. If most conscious experiences are Boltzmann hallucinations, how can we trust that our memories, laws of physics, or even the passage of time aren't just fleeting glitches in the foam? But before you question everything, there's a counter-argument, the anthropic principle. Roughly, it states that we find ourselves in a universe capable of sustaining life because, well, we couldn't observe one that doesn't. A Boltzmann brain's experience would be statistically more likely, but also incoherent, a jumble of false memories with no consistent reality to ground it. By contrast, our ordered universe, though improbable, allows for stable, long-lived observers who can actually ponder these questions. In other words, the mere fact that we're having this discussion suggests we're probably not Boltzmann brains. The debate gets thornier when cosmology enters the mix. If dark energy keeps accelerating the universe's expansion, eventually all matter will be torn apart in a big rip, leaving only empty space churned by quantum foam. In that distant epoch, Boltzmann brains might become the only observers left, outlasting galaxies, stars, and even atoms. Some physicists argue this makes their existence unavoidable, a chilling prospect that forces us to confront whether consciousness itself is a cosmic accident or something deeper. Ultimately, the paradox isn't just a thought experiment, it's a stress test for our understanding of reality. Quantum foam's turbulence doesn't just warp space and time, it warps what we think we know about existence. And while the odds of a Boltzmann brain forming in your coffee cup right now are vanishingly small, the sheer scale of eternity means the foam might yet have a few surprises tucked in its chaotic depths. Quantum foam might be more than just chaos, it could be the universe's ultimate error-correcting system, silently protecting reality from glitches that would otherwise tear it apart. This mind-bending theory suggests that spacetime's frothy turbulence isn't random noise but a highly organized code, one that constantly repairs and stabilizes the fabric of existence. Think of it like a cosmic hard drive. Just as your computer uses error correction to stop a scratched DVD from skipping, quantum foam could be performing trillions of microscopic repairs every second, ensuring the universe doesn't crash from quantum-level corruption. At the heart of this idea lies holography, a radical principle born from string theory and black hole physics. The AD-S/CFT duality, a groundbreaking mathematical framework, proposes that our three-dimensional universe might be encoded on a two-dimensional surface like a cosmic hologram. In this view, every particle, every force, even spacetime itself is just a projection from deeper, hidden layers of reality. Quantum foam emerges as the glue holding this projection together, its fluctuations acting like error-correcting algorithms that patch up inconsistencies before they can destabilize the cosmic code. Black holes put this to the ultimate test. When matter falls into a singularity, classical physics says it's destroyed forever, but quantum mechanics insists information can't be lost. The infamous firewall paradox pits these two ideas against each other, suggesting a wall of searing energy might vaporize anything crossing the event horizon. But if quantum foam is nature's error correction, it could resolve the paradox by subtly encoding the doomed matter's information into the foam's structure, preserving it in spacetime's quantum fluctuations. It's like burning a book but scattering its ashes in a pattern that still holds every word waiting to be decoded. The parallels to technology are eerie. Modern quantum computers use error-correcting codes to shield fragile qubits from decoherence, wrapping them in layers of redundancy. Quantum foam might do the same for the universe, its turbulent geometry providing just enough redundancy to prevent cosmic-scale crashes. Even stranger, some models suggest this correction isn't passive, it's dynamic, with the foam actively rewriting spacetime's fabric to smooth out inconsistencies, like an autocomplete function for reality. Critics argue this stretches analogy too far, conflating abstract math with physical mechanisms. Yet supporters point to tantalizing clues, like how black hole entropy calculations mirror error-correcting code structures almost exactly. Future experiments like precision tests of quantum entanglement in high-energy collisions might reveal whether spacetime truly checksums itself against errors. If so, it would mean the universe isn't just stable by accident, it's stable by design, with quantum foam as its silent, ceaseless maintenance crew. The implications are staggering. If foam corrects errors, it could explain why the universe hasn't dissolved into quantum noise over billions of years. It might even hint that reality is fundamentally computational, an idea that dovetails with simulation hypotheses. But perhaps most beautifully, it suggests that beneath the chaos we perceive, there's an order so profound, so precise, that it keeps the cosmos running smoothly, one plank-sized patch at a time. What if the quantum foam beneath spacetime harbors structures that move without energy, defying one of the universe's most sacred laws? The answer might lie in time crystals, a bizarre form of matter that repeats in time rather than space, creating perpetual motion at the quantum level. First theorized in 2012 and realized in labs just 5 years later, time crystals don't just exist, they tick like microscopic clocks cycling through states with no energy input. Now imagine this phenomenon scaled down to Planck-sized realms, where quantum foam's turbulence could birth time crystalline structures flickering in the void. It's a dizzying possibility that spacetime itself might contain pockets of eternal rhythm whispering beneath the chaos. The magic of time crystals lies in their broken symmetry. Normal crystals like diamonds or salt have atoms arranged in repeating spatial patterns. Time crystals flip this, exhibiting patterns that repeat in time, oscillating between configurations indefinitely without friction or decay. In 2017, researchers created the first time crystal using chains of ytterbium atoms, nudged into this strange state with laser pulses. Even more astonishing, when Google's quantum computer Sycamore simulated a time crystal in 2021, it kept cycling for hundreds of cycles with no energy loss, like a pendulum that never stops swinging. If this can happen in a lab, why not in nature? Quantum foam's seething energy landscape could provide the perfect cradle for spontaneous time crystalline order, with spacetime's fluctuations acting as the nudges that keep these structures ticking. The implications are staggering. If time crystals exist in quantum foam, they defy the second law of thermodynamics, not by creating energy from nothing, but by exploiting a loophole where motion requires no energy at all. Picture a whirlpool in a stream that never dissipates, not because it's powered, but because the water's flow naturally sustains it. Similarly, a foam-borne time crystal might tap into spacetime's inherent vibrations, locking into a stable rhythm immune to entropy. Some theories suggest these structures could even act as cosmic clocks, marking time in the early universe before stars or atoms formed, their oscillations imprinting faint echoes in the fabric of reality. There's a catch, of course. Lab-made time crystals rely on carefully controlled conditions, while quantum foam is the definition of chaos. Skeptics argue that foam's turbulence would shred any delicate time crystalline order before it could stabilize. But supporters counter that certain foam models like loop quantum gravity predict regions where spacetime's granularity could enhance coherence, creating pockets of unexpected stability. It's akin to how rough seas can still produce fleeting moments of calm where waves cancel each other out. If true, time crystals might not just survive in the foam, they could be inevitable, woven into spacetime's deepest structure. The real allure is what these crystals could do. If harnessed, they might offer a backbone for quantum memory, preserving information in their unyielding cycles. Or they could serve as probes into the early universe, their rhythms encoding data from epochs long before light began to shine. Some even speculate that time crystals could stabilize wormholes, their perpetual motion counteracting the gravitational forces that would otherwise collapse these spacetime tunnels. But the wildest idea, that time crystals aren't just in the foam, they are the foam, spacetime's fundamental jitter crystallizing into patterns that repeat across eternity. For now, this remains speculative poetry, dancing at the edge of theory and experiment. But as labs push time crystal research further, they might inadvertently test quantum foam's wildest possibilities. Every flicker of a synthetic time crystal could be a glimpse into nature's hidden rhythms, hinting that beneath the chaos, the universe keeps perfect time. At the smallest scales imaginable, where quantum foam churns and twists, the universe might not just be turbulent, it could be repeating itself. The idea that spacetime's foam exhibits fractal geometry is one of the most visually stunning and mathematically profound theories in modern physics. Fractals, those infinitely complex patterns that look similar at any magnification, are nature's way of building complexity from simple repetition. Think of a snowflake's branching arms or a coastline's jagged edges. But if quantum foam shares this property, it would mean that no matter how deep you zoom into the fabric of reality, you'd encounter the same swirling, self-similar structures, like a cosmic hall of mirrors reflecting chaos at every level. This isn't just poetic speculation. Certain models of quantum gravity, like loop quantum cosmology and causal dynamical triangulations, suggest that spacetime's foam-like nature could indeed be fractal. In these frameworks, the universe isn't just granular, it's recursive, with tiny Planck-scale fluctuations echoing the behavior of much larger cosmic structures. Imagine zooming in on a fractal fern. Each tiny leaf resembles the whole plant. Similarly, if you could peer into a speck of quantum foam, you might see a whirlpool of spacetime that, at a different scale, mirrors the spin of a galaxy or the vortex of a black hole's accretion disk. The implication: the universe might not have distinct, large, and small regimes, just layers of the same geometric dance playing out across infinite dimensions. The stakes are high. If spacetime is fractal, it could rewrite our understanding of dimensionality itself. We're used to thinking in 3 dimensions of space and 1 of time, but a fractal foam might blur those lines, suggesting that dimensions aren't fixed but emerge from the foam's complexity. Some theories propose that what we perceive as smooth, continuous space is actually a projection of deeper fractal layers, like a hologram where higher dimensions are encoded in lower ones. This could explain why gravity, the force that shapes galaxies, feels so weak compared to other forces at quantum scales. In a fractal foam, gravity might leak across dimensional boundaries, diluting its strength as it filters through nested layers of spacetime. Critics argue that fractal foam models are hard to test since we can't yet probe the Planck scale directly, but supporters point to surprising hints in cosmology. The large-scale structure of the universe, the web of galaxies and voids stretching across billions of light-years, bears an uncanny resemblance to fractal patterns seen in quantum simulations. Even the distribution of matter in the cosmic microwave background shows fluctuations that some physicists argue mirror the self-similarity expected from a fractal spacetime. It's as if the universe is whispering its geometry to us if only we know how to listen. The most tantalizing possibility, fractal foam might offer a bridge between the quantum and cosmic realms, revealing that the universe's grandest structures and tiniest tremors are two sides of the same coin. If so, then every time you look at the night sky, you're not just seeing stars, you're glimpsing a reflection of spacetime's hidden symmetry, a pattern etched into the void at every scale, from the smallest bubble of quantum foam to the vast expanse of the cosmos itself. The Higgs field gets all the credit for giving particles mass, but what if quantum foam has been pulling the strings all along? This provocative theory suggests that spacetime's turbulent froth might play a hidden role in determining why some particles are heavy while others weigh almost nothing. Picture the quantum vacuum not as a static backdrop, but as a stormy ocean where particles are like boats, some cut smoothly through the waves, barely slowed, while others get tossed violently, their motion weighed down by the foam's churn. This resistance could be more than just friction. It might be the origin of mass itself, woven into the fabric of spacetime. The standard Higgs mechanism explains mass beautifully. For most particles, they gain weight by interacting with the Higgs field, like wading through molasses. But some physicists argue quantum foam could offer a parallel pathway, especially for particles that don't fit neatly into the standard model. Take neutrinos. These ghostly particles have minuscule masses that the Higgs mechanism struggles to explain. If foam's fluctuations interact differently with various particles, creating unique drag effects, it could account for these anomalies. Imagine throwing two balls into that stormy ocean, one light and buoyant, the other dense. The foam's turbulence would slow them unevenly, mimicking distinct masses without needing a universal Higgs molasses. The math gets wild here. Certain quantum gravity models predict that foam's Planck scale bubbles create transient gravitational fields, microscopic hills and valleys that particles must climb or descend. Each interaction would sap energy, making the particle act as if it has inertia. This isn't entirely unlike Einstein's revelation that gravity warps spacetime, but scaled down to the realm where spacetime itself is frothing. Some calculations even suggest that at ultra-high energies, like those right after the Big Bang, these foam-induced mass effects could dominate, temporarily sidelining the Higgs entirely. It's as if the universe had two competing systems for assigning mass, one for calm seas and another for when the quantum ocean rages. Critics bristle at the idea. The Higgs mechanism is exquisitely precise, validated by countless experiments, including the monumental discovery of the Higgs boson at CERN. Why complicate things? Yet foam enthusiasts point to lingering puzzles, like why the top quark is ludicrously heavier than the electron, or why dark matter particles, if they exist, might ignore the Higgs entirely. If foam contributes even a fraction to these mass hierarchies, it would force a rewrite of particle physics' foundational rules. The implications ripple further. If mass emerges from foam's turbulence, then black holes, neutron stars, and other extreme objects might warp mass itself near their event horizons, where spacetime's froth is stretched to breaking point. Experiments are already hunting for clues. Ultra-precise measurements of neutrino masses could reveal deviations from Higgs predictions, hinting at foam's subtle influence. Particle colliders probing energies closer to the Planck scale might spot anomalies in how quarks and leptons gain weight. Even gravitational wave detectors could play a role if foam affects mass. Merging black holes might shudder in ways that betray spacetime's granularity. The stakes, a universe where mass isn't handed down by a single cosmic field, but negotiated in the chaotic marketplace of quantum foam. Particles wouldn't just have mass, they'd earn it through a dynamic dance with spacetime's deepest turbulence. And if that's true, then every atom in your body isn't just borrowing weight from the Higgs, it's surfing the froth of reality itself. Neutrinos are the universe's ultimate shape-shifters, particles so elusive they can pass through light years of lead without a single collision. But their strangest trick, they change identities mid-flight, oscillating between three flavors: electron, muon, and tau neutrinos. For decades, physicists assumed this metamorphosis was purely a quantum mechanical effect. Yet some theorists suspect something deeper might be at play, that the quantum foam beneath spacetime could be subtly twisting neutrinos' paths, influencing their transformations in ways we're only beginning to uncover. The math behind this is as elegant as it is radical. Neutrino oscillations arise because the flavors we detect aren't the particle's true mass states but quantum superpositions, mixtures that evolve as they travel. Traditional models attribute this to neutrino mass differences and weak force interactions, but add quantum foam's turbulence and the story gets richer. Imagine a neutrino streaking through space. As it encounters Planck-scale fluctuations in the foam, spacetime's churning geometry might nudge its quantum phase, the internal rhythm that dictates its flavor. Over cosmic distances, these tiny nudges could accumulate, altering oscillation patterns in ways standard physics can't explain. It's like a hiker crossing a mountain range. The terrain's bumps might not change their destination, but they'll sure affect the path they take. Experimental hints are already stirring intrigue. The Ice Cube Neutrino Observatory in Antarctica has detected high-energy neutrinos from distant galaxies whose oscillation patterns don't quite match predictions. Some exhibit slight delays or excesses in flavor transitions that align with models where foam-induced spacetime jitter plays a role. Even more tantalizing are anomalies in reactor neutrino experiments, where detectors near nuclear plants record fewer electron neutrinos than expected. A discrepancy foam theories might explain if spacetime's granularity scrambles their phases en route. Critics argue these anomalies could stem from mundane sources, calibration errors, incomplete models of neutrino interactions, or even undiscovered particle physics. But foam proponents counter that the sheer scale of neutrino journeys amplifies foam's potential influence. A neutrino born in a supernova travels billions of light years before reaching Earth, giving Planck scale effects trillions of chances to leave a mark. It's the ultimate needle in a haystack scenario. Spacetime's tiniest wrinkles might only reveal themselves when threaded across the cosmos. The stakes are cosmic. If foam affects neutrino oscillations, it wouldn't just tweak particle physics, it could redefine how we map the universe. Neutrinos are messengers from the most violent events in existence: supernova, merging neutron stars, active galactic nuclei. If their flavors are being subtly reshaped by spacetime's foam, our interpretations of these events, their energies, distances, even the nature of dark matter, might need recalibration. Future experiments like the Deep Underground Neutrino Experiment (DUNE) could settle the debate by tracking neutrinos with unprecedented precision, hunting for statistical deviations that foam's fingerprints would leave behind. The wildest implication, neutrinos might be more than particles. They could be probes carrying encrypted notes about spacetime's quantum structure. Every oscillation, every flavor shift might encode secrets about the foam's texture waiting to be decoded. In this light, neutrinos aren't just cosmic ghosts, they're the universe's whispered confessions, telling us how spacetime really behaves when no one's looking. String theory whispers of a universe far richer than we see, one with not just 3 dimensions of space but 10 or more, curled up so tightly they're hidden from view. But if these extra dimensions exist, where are they? The answer might lie in the quantum foam's chaotic dance, where spacetime's tiniest fluctuations could be twisting reality into shapes we've barely begun to imagine. Picture a garden hose lying on the ground. From a distance, it looks like a simple line, one dimension, but zoom in close and you'd see its circular cross-section, a second dimension curled so tightly it's invisible at larger scales. Now shrink that idea by a factor of 1 trillion, and you've got the compactified dimensions. String theory proposes tiny loops and folds woven into the fabric of spacetime itself, potentially lurking within the foam's Planck-scale turbulence. The foam's role here is tantalizing. If spacetime is frothing with microscopic bubbles of energy, those bubbles could be the very places where extra dimensions pinch off or fold in on themselves like origami crumpled at unthinkably small scales. Certain string theory models suggest that the foam's violent fluctuations might stabilize these compactified dimensions, preventing them from unraveling. It's as if the foam's chaos acts as cosmic glue, holding the extra dimensions in place while the 3 we experience stretch out across the universe. This wouldn't just be a mathematical curiosity, it could explain why gravity feels so weak compared to other forces. If gravitons, the hypothetical particles carrying gravity, can leak into these extra dimensions, their strength would dilute as they spread through higher dimensional space, like light dimming as it radiates outward in all directions. Testing this idea isn't easy, but physicists have devised ingenious experiments. One approach involves hunting for deviations in gravity at microscopic distances. If extra dimensions are tucked into the foam's structure, Newton's inverse square law, which says gravity weakens with the square of the distance, should break down at scales comparable to those dimensions' size. Think of it like listening for echoes in a hallway. If there's a hidden alcove, an extra dimension, sound waves, or in this case, gravitational forces would behave differently than in an open space. Experiments using exquisitely sensitive torsion balances, like those at the University of Washington's EarthWash lab, have probed gravity down to micrometer scales, searching for anomalies that might betray extra dimensions. So far, no smoking gun, but the hunt continues. Another avenue involves high-energy particle collisions. If extra dimensions are curled up in the foam, smashing protons together at near light speeds in machines like the Large Hadron Collider could momentarily unfurl them, creating fleeting gravitational effects or even microscopic black holes. These wouldn't be the planet-swallowing monsters of sci-fi. They'd evaporate instantly via Hawking radiation, leaving behind telltale patterns in detector data. While no such signatures have been confirmed yet, the fact that we can even conceive of these experiments speaks to how deeply quantum foam and extra dimensions might be intertwined. The wildest implication: if foam hides extra dimensions, it could mean we're surrounded by unseen structures, tiny loops, braids, and folds everywhere we look. The empty space around you, the air you breathe, even the gaps between atoms in your hand might be teeming with geometric complexity, all vibrating just beyond our perception. It's a humbling thought that the universe's full splendor might be tucked into the turbulence beneath our feet, waiting for the right experiment, the right moment to reveal itself. The Pioneer probes, humanity's first interstellar emissaries, carried our ambitions beyond the solar system, but their journey held a mystery no one saw coming. As these spacecraft hurtled toward the stars, scientists noticed something bizarre. Both Pioneer 10 and 11 were slowing down ever so slightly, as if an invisible hand were tugging them backward. The deceleration was tiny, just a fraction of a nanometer per second squared, but it defied every known force in physics. This became known as the Pioneer anomaly, a puzzle that lingered for decades. Now imagine if the answer wasn't some exotic force or unseen matter, but the quantum foam beneath spacetime itself, subtly dragging on the probes like cosmic molasses. At first glance, quantum foam seems too delicate to affect something as massive as a spacecraft. But think of it like sailing through an ocean filled not with water, but with microscopic whirlpools. Each Planck-sized fluctuation in spacetime's foam could exert a minuscule gravitational tug on the pioneers as they passed through it. Over billions of kilometers, these trillions upon trillions of interactions might add up to the observed deceleration, a kind of foam drag akin to how air resistance slows a car, but operating on scales so small we've never directly observed it. The math is speculative but tantalizing. If foam's turbulence creates transient pockets of altered gravity, even a slight bias in their distribution could produce a net-breaking effect over immense distances. Of course, not everyone buys the foam explanation. For years, the leading theory blamed thermal radiation, the simple idea that heat radiating unevenly from the probe's power sources could nudge them off course. In 2011, a team analyzing decades of telemetry data concluded that asymmetrical heat flow from Pioneer's plutonium batteries matched the anomaly's profile almost perfectly. Case closed, not quite. While thermal radiation explains much of the deceleration, some researchers argue it doesn't account for all of it. There's a stubborn residual effect, a whisper of something else at play, and that's where quantum foam slides back into the picture. Here's where things get wild. If foam drag is real, it wouldn't just affect the pioneers. Every spacecraft Voyager, New Horizons, even distant starships of the future, might experience a similar, almost imperceptible drag as they slice through spacetime's frothy undercurrent. The effect would be vanishingly small for missions within the solar system, but for interstellar voyages spanning centuries, it could compound into significant course deviations. Some theorists even speculate that foam drag might one day serve as a tool, a way to map the granularity of spacetime by comparing the trajectories of ultra-precise probes. The debate isn't just about solving a decades-old mystery. It's a proxy war for how we understand the universe at its most fundamental level. If thermal radiation fully explains the Pioneer anomaly, it reinforces classical physics power to solve problems without invoking exotic theories. But if quantum foam claims even a fraction of responsibility, it's a smoking gun, evidence that spacetime's turbulence has measurable consequences far beyond the quantum realm. Future missions like Breakthrough Starshot's light sail probes might settle the argument by measuring acceleration with unprecedented precision, hunting for deviations that foam's whispers would leave behind. Until then, the Pioneer anomaly remains a cosmic riddle wrapped in a quantum enigma. Whether the answer lies in mundane heat or spacetime's hidden froth, one thing's certain: the universe loves to remind us that even our boldest explorations are just scratching the surface of reality's deepest mysteries. Quantum tunneling defies common sense, particles vanishing through barriers they shouldn't have the energy to cross, like ghosts walking through walls. But what if spacetime's quantum foam is the unseen hand guiding this bizarre phenomenon? At the smallest scales, where foam's turbulence twists spacetime into fleeting hills and valleys, particles might not just tunnel, they could be surfing hidden contours in reality's fabric. This isn't just theoretical whimsy. If foam alters tunneling rates, it could revolutionize everything from star-bound fusion reactors to unhackable quantum encryption. Take nuclear fusion, the process that powers stars but has eluded our control for decades. In labs, forcing atomic nuclei to merge requires temperatures hotter than the sun's core to overcome their mutual repulsion. Yet tunneling offers a shortcut. A tiny chance nuclei will bypass that barrier entirely. Quantum foam could tilt those odds. If foam fluctuations create microscopic gravitational dips or spikes, they might act like cosmic ramps, nudging particles closer together and boosting tunneling probabilities. Some models suggest this effect could lower the energy needed for fusion, turning sci-fi dream reactors into practical power sources. Imagine a world where clean, limitless energy doesn't require recreating a star's fury, but harnessing spacetime's hidden topography instead. Quantum computing faces the opposite challenge. Qubits, the fragile heart of quantum processors, rely on controlled tunneling to maintain superposition. But too much tunneling causes leakage, where information decays into noise. Here, foam's chaos might be the villain. Random spacetime fluctuations could jostle qubits mid-calculation, accelerating decoherence. Recent experiments at labs like Google Quantum AI hint at this. Certain error patterns in qubit behavior align eerily with models of Planck-scale spacetime noise. Yet there's a twist. If we could map foam's influence, we might engineer qubits to exploit it, designing tunneling pathways that sync with spacetime's natural rhythms for unprecedented stability. The implications stretch further. Some theories posit that foam-enabled tunneling could explain dark matter's elusiveness. What if certain particles don't just rarely interact with matter, but tunnel through it effortlessly, slipping between foam's gaps like fish through a net? Even biology isn't immune. Enzymes, nature's molecular machines, rely on tunneling to speed up life-critical reactions. If spacetime's microscopic texture affects these rates, quantum foam might quietly shape the very chemistry of life. The frontier lies in testing these ideas. Projects like ITER fusion reactor could reveal if plasma behaves in ways that betray foam's hand. While next-gen quantum computers might double as foam detectors, their qubits sensitive to spacetime's faintest tremors. One thing's certain: the universe's smallest turbulence could rewrite the rules of the largest breakthroughs. Gravitational waves, ripples in spacetime from colliding black holes and neutron stars, have opened a new window onto the cosmos. But what if these signals carry more than just the echoes of distant cataclysms? Hidden within their delicate waveforms might be the faint static of quantum foam, a whisper of spacetime's turbulent undercurrent. As detectors grow more sensitive, physicists are racing to predict whether they'll find this elusive noise, a discovery that could reveal reality's granular fabric. The challenge is staggering. Quantum foam's fluctuations occur at the Planck scale, a realm a billion times smaller than the wavelengths of gravitational waves we currently detect. To spot foam's fingerprints, future observatories like the Einstein telescope or Cosmic Explorer would need sensitivity so precise they could measure displacements smaller than an atom's nucleus across distances light-years long. But here's the twist: foam wouldn't just add noise uniformly. Its chaotic froth would imprint distinctive statistical anomalies, tiny deviations in wave phase or amplitude that betray spacetime's underlying graininess. Imagine listening to a symphony where every so often a single note wavers imperceptibly because the violin's wood has microscopic cracks. The music plays on, but the flaws hint at a deeper structure. Competing noise sources muddy the waters. Thermal vibrations in detector mirrors, seismic tremors, even quantum jitter in laser photons all mimic the random fluctuations foam would create. Separating the cosmic signal from earthly interference requires ingenious filtering. One strategy involves comparing signals from multiple detectors. If foam noise is universal, it should appear consistently across widely spaced observatories, while local noise won't correlate. Another approach exploits foam's predicted frequency dependence. Its effect should grow more pronounced at higher frequencies, where shorter wavelengths probe smaller spacetime scales. The wild card: neutron-star mergers. These collisions produce gravitational waves across a broad spectrum, including high-frequency components that black hole mergers lack. A 2030s-era detector network might catch these signals with enough clarity to spot Planck-scale distortions. Some models even suggest foam could subtly alter the wave's polarization, a smoking gun, if the pattern matches quantum gravity predictions. Critics argue the quest is premature. Without a unified theory of quantum gravity, we can't be sure what foam's noise should look like. But supporters counter that absence of evidence isn't evidence of absence. If detectors keep improving without finding foam's trace, it could mean spacetime is smoother than quantum theory predicts, a revelation just as revolutionary. The stakes transcend gravitational waves. If foam's noise is real, it would prove spacetime isn't a stage but a participant, a dynamic entity with its own quantum personality. And if not, the silence would speak volumes, forcing us to rethink reality's deepest foundations. Either way, the hunt is on and the cosmos is listening. The black hole firewall paradox is one of physics' most explosive debates, a thought experiment that threatens to rewrite Einstein's theory of general relativity with a wall of searing radiation at the event horizon. But quantum foam might hold the key to extinguishing this cosmic blaze. The paradox begins with a simple question: what happens to information swallowed by a black hole? Quantum mechanics insists it can't be destroyed, yet relativity predicts it's crushed beyond recovery at the singularity. In 2012, theorists proposed a brutal compromise, an annihilating firewall of high-energy particles at the event horizon, vaporizing anything crossing it. The catch: this violates relativity's core tenet that free-falling observers should experience nothing unusual at the horizon. Enter quantum foam, whose turbulent geometry could offer a far gentler solution. Picture an astronaut approaching a black hole's boundary. Classical physics says they'd float through unharmed, blissfully unaware of the point of no return. Firewall advocates argue quantum effects would shred them with radiation instead. But foam-based models suggest a third path. Spacetime's Planck-scale turbulence could blur the horizon itself, transforming it from a sharp boundary into a swirling, fractal-like zone where gravity's grip fluctuates wildly. In this view, the firewall isn't a singular wall but a diffuse haze of quantum noise, like static fizzing at the edge of a radio signal. The astronaut wouldn't be incinerated, they'd be gently scrambled, their quantum states subtly mixed by foam's churn without catastrophic violence. This idea gains traction from holographic principal mathematics, which treats the event horizon as a buzzing hologram encoding all the black hole's information. Quantum foam's fluctuations could be the mechanism writing that data, each Planck-sized bubble acting like a pixel storing bits of the astronaut's configuration as they cross. Instead of burning up, they'd undergo a gradual, pixelated transformation, their information smeared across the horizon's frothy surface like ink dissolving in turbulent water. Supporting this, some loop quantum gravity simulations show horizon regions where spacetime's granularity becomes dominant, smoothing the violent discontinuities firewall theories predict. Critics counter that foam's smoothing effect might be too subtle to fully resolve the paradox. After all, information preservation demands precision. Random noise won't suffice. Yet foam enthusiasts highlight an elegant loophole: entanglement. If the foam's dynamics naturally entangle infalling matter with outgoing Hawking radiation, as recent AD/CFT calculations suggest, it could preserve information without firewalls. Imagine the horizon not as a one-way shredder but as a quantum loom, weaving incoming particles into spacetime's fluctuations while spitting out entangled radiation. A cosmic recycling plant where nothing is lost, only rearranged. The debate hinges on a deeper mystery: does quantum foam erase singularities entirely? If spacetime's granularity prevents infinite density, as loop quantum cosmology proposes, there'd be no need for firewalls to begin with. An evaporating black hole might leave behind a dense, foam-like remnant, a Planck-scale nugget encoding all the original information, humming quietly in the void. Upcoming gravitational wave observations could tilt the scales. Colliding black holes' ring-down phases might carry echoes of foam-modified horizons, revealing whether firewalls exist or if spacetime's turbulence keeps the peace after all. One thing's certain: the universe's most destructive objects might owe their harmony to the quantum chaos beneath. Quantum foam might not just be spacetime's turbulent foundation, it could be a cosmic thermal engine, humming with hidden entropy and temperature. This startling idea reshapes how we think about the vacuum of space, treating it not as an icy void but as a seething thermodynamic system, where every Planck-sized bubble carries the faintest whisper of heat. Picture the foam as a vast, churning ocean where energy constantly redistributes itself, not through conventional heat transfer, but through the relentless creation and annihilation of virtual particles and spacetime fluctuations. If foam has thermodynamic properties, it would bridge two of physics' greatest mysteries, the quantum nature of gravity and the stubborn arrow of time. Start with entropy, the measure of a system's disorder. Black holes famously possess entropy proportional to their event horizon's area, a discovery that revolutionized our understanding of gravity and information. Quantum foam could extend this idea to the fabric of spacetime itself. If each microscopic bubble in the foam encodes a tiny bit of information, like a pixel in a cosmic image, then spacetime's total entropy might emerge from the sum of these chaotic, flickering bits. Some theories suggest this entropy isn't static. It fluctuates as the foam's structure evolves, creating a dynamic dance where disorder ebbs and flows at scales we're only beginning to fathom. Temperature enters the picture through Hawking radiation. Just as black holes glow with heat due to quantum effects at their horizons, quantum foam's turbulent geometry might generate thermal signatures of its own. Imagine spacetime's froth as a lattice of microscopic black holes and white holes, each emitting and absorbing energy in a frenetic exchange. The foam's average temperature would be unimaginably cold, just billionths of a degree above absolute zero, but its existence would imply something profound. The vacuum isn't empty. It's a thermal bath vibrating with energy at the smallest scales. The connection to time's arrow is where things get truly mind-bending. Thermodynamics dictates that entropy tends to increase, giving time its one-way flow. If foam's entropy is fundamental, it could mean time's direction isn't just a consequence of the Big Bang's initial conditions, but woven into spacetime's very structure. The foam's ceaseless churn would act like a cosmic ratchet, nudging the universe toward higher disorder with every Planck second that passes. Some models even speculate that in regions where foam's fluctuations become extreme, like near a singularity, time's arrow might falter or reverse, a fleeting breakdown of causality in the quantum storm. Critics argue that assigning temperature and entropy to foam is speculative, lacking direct experimental support. Yet experiments like the Casimir effect, where quantum fluctuations exert measurable forces, hint that the vacuum does behave like a thermodynamic system, brimming with energy waiting to be tapped. Future probes, like ultra-precise measurements of cosmic microwave background fluctuations or quantum simulations of spacetime's granularity, might reveal foam's thermal fingerprints. The implications ripple across physics. If foam is thermodynamic, it could explain why the universe began in a low entropy state, a prerequisite for life's existence. It might also redefine dark energy, casting it not as a mysterious field but as the foam's thermal equilibrium, a steady-state hum of spacetime's quantum vibrations. And if we ever learn to manipulate foam's thermodynamics, we could unlock technologies that harness vacuum energy or even tweak the flow of time itself. For now, quantum foam's thermal nature remains a compelling hypothesis, a reminder that even the coldest depths of space might be alive with heat, if only we know where to look. Ultra-high-energy cosmic rays streak across the universe with energies so immense, they make particle accelerators like the Large Hadron Collider look like toys. Some pack the kinetic energy of a baseball in a single subatomic particle. For decades, scientists traced these cosmic bullets back to violent events like supernova or colliding galaxies. But there's a catch. The most energetic rays exceed theoretical limits for how fast magnetic fields in these environments can boost particles. The mystery has led some physicists to an audacious alternative. What if these rays aren't accelerated by astrophysical cataclysms at all, but born from the quantum foam's raw turbulence? Picture spacetime's foam as a frothing ocean during a storm, where Planck-scale bubbles aren't just empty fluctuations but potential particle foundries. In certain models of quantum gravity, foam's violent churn could concentrate energy into microscopic regions, twisting spacetime so severely that it spontaneously ejects particles with absurd energies. Think of it like squeezing a water balloon until it bursts, except instead of water, you're releasing a proton with the energy of a professional fastball. These particles wouldn't need gradual acceleration. They'd emerge fully energized from the foam's chaotic depths like sparks flying from a grinding wheel. The math behind this is as elegant as it is speculative. If foam's fluctuations create transient wormholes or warp spacetime into microscopic black holes, even for fractions of a second, their gravitational collapse could convert vacuum energy directly into particle beams. Unlike supernova, which rely on shockwaves to progressively speed up particles, foam-based mechanisms would operate instantly, bypassing the speed limits imposed by magnetic fields. This could explain cosmic rays with energies beyond 10 to the 20th electron volts, particles so powerful they shouldn't exist under conventional astrophysics. Critics aren't convinced. Traditional acceleration models, though stretched to their limits, can account for most cosmic rays through processes like Fermi acceleration in supernova remnants or active galactic nuclei. Detectors like the Pierre Auger Observatory have even traced some ultra-high-energy rays back to distant quasars, undermining the need for exotic foam origins. But supporters counter that these tracings aren't definitive. Intergalactic magnetic fields scramble particle paths, making precise pinpointing impossible. And for the very highest energy events which arrive too rarely to map reliably, foam remains a tantalizing wildcard, the smoking gun, a telltale signature in the ray's composition. If foam spawns cosmic rays directly, they might carry unusual features, an overabundance of certain particle types, or energy distributions that don't match astrophysical predictions. Some theorists even suggest these particles could arrive in bursts, clustered in ways that reflect foam's sporadic, localized energy releases. Future observatories like the planned Cherenkov telescope array could hunt for these anomalies with unprecedented precision. The stakes are cosmic. If foam generates even a fraction of ultra-high-energy rays, it would mean the universe's most energetic phenomena aren't just out there in the stars. They're woven into the fabric of reality itself, erupting from the quantum depths beneath our feet. Every time a cosmic ray pierces Earth's atmosphere, it might carry not just the fingerprints of distant explosions, but the echoes of spacetime's restless, frothing heart. Quantum foam may seem like an immutable feature of spacetime, but as the universe ages, even this frenetic underpinning of reality could face transformative change. The fate of quantum foam ties directly into cosmology's grandest questions: whether the cosmos will fade into eternal silence, rip itself apart, or perhaps even reset in a cyclical rebirth. Consider heat death first, the scenario where the universe expands forever, stars burn out, and all matter succumbs to entropy. In this bleak future, quantum foam wouldn't vanish, but its seething energy could thin into a faint whisper. With galaxies dispersed to oblivion and spacetime stretched to near-perfect smoothness, the foam's fluctuations might lose their vigor, like a stormy sea calming into gentle ripples. Yet even in this frozen era, the foam's latent energy could linger as the universe's last flicker of activity, a ghostly murmur in an otherwise silent void. Some theories suggest that over unfathomable timescales, quantum tunneling within the foam might spark sporadic rebirths, random bubbles of false vacuum decay, spawning new universes in an otherwise dead cosmos. The Big Rip offers a far more violent finale. If dark energy's repulsive force grows stronger over time, it could eventually overpower all cosmic structures, first galaxies, then stars, planets, and finally even atoms. Quantum foam wouldn't escape this carnage. As spacetime's expansion accelerates beyond all limits, the foam's Planck-scale fabric could be stretched apart, its fluctuations torn into incoherence. Picture a tapestry unraveling thread by thread until no weave remains. In this scenario, foam wouldn't just fade, it would shatter, leaving spacetime as a fractured, meaningless void where not even quantum connections hold. But there's a third possibility: cyclic cosmology. If the universe follows an endless loop of expansion and contraction, quantum foam could be the cosmic recycler, resetting with each new cycle. During a big crunch, spacetime's collapse might compress the foam to unimaginable densities, its fluctuations merging into a singularity only to rebound in a new Big Bang, frothing back into existence with fresh turbulence. Some models even propose that the foam retains subtle imprints from past cycles, like cosmic DNA passing traits between universes, the wild card, dark energy's unknown nature. If it evolves unpredictably, quantum foam could undergo phases of reinvigoration or decay we can't yet foresee. Imagine foam freezing into a crystalline lattice in one epoch, only to melt back into chaos later. The universe's deepest fate might hinge on these microscopic seethings, proof that even in the grandest cosmic story, the smallest details write the final chapter. From microscopic wormholes flickering in the void to spacetime itself remembering black holes' secrets, quantum foam has taken us on a journey that rewrites everything we thought we knew about reality. We've seen how this turbulent sea beneath the cosmos could power universal expansion, birth rogue cosmic rays, even forge fleeting pockets of consciousness from pure chaos. Each theory peels back another layer of the universe's strangeness, revealing a world where emptiness seethes with hidden activity, where the fabric of existence is less a smooth stage and more a storm of infinite possibilities. Consider the sheer audacity of these ideas. Black holes might not be cosmic dead ends but holographic vaults, their event horizons pixelated libraries written in spacetime's quantum static. The arrow of time could emerge from the foam's ceaseless churn, while dark matter might just be the hidden topography of spacetime's uneven froth. And perhaps most dizzying of all, the universe we inhabit might owe its very existence to the foam's primordial turbulence, a cascade of quantum fluctuations that set the stage for galaxies, stars, and curious minds to ponder it all. This isn't just science, it's a revolution in how we perceive reality. Quantum foam forces us to confront uncomfortable truths, that space isn't empty, time isn't uniform, and that laws of physics might be local ordinances in a far weirder cosmos. It humbles us, the very ground beneath your feet, the air you breathe, the light from your screen. All of it rests atop a quantum undercurrent we're only beginning to map. Now it's your turn. Which theory twisted your mind the most? Were you captivated by the possibility of spacetime's fractal depths? Or did the idea of Boltzmann brains hallucinating reality give you existential chills? Drop your favorite in the comments. I read every one. And if today's dive into the foam left you hungry for more cosmic mysteries, hit that subscribe button. We've got wormholes to stabilize, multiverses to explore, and a universe's worth of wonders waiting just beyond the next click. Until then, keep looking deeper. Because the wildest truths, they're hiding in plain sight, woven into the quantum fabric of everything.